Hello, everyone. Today I'm going to talk about quantum computing based on semiconductors. This is Jing Guo, and from Department of ECE at University of Florida. So first, I'll give an overview of quantum computing and briefly review the history and recent progress. Then I'm going to discuss semiconductor-based quantum computing. And finally, we'll quickly talk about modeling and simulation for semiconductor-based quantum computing. So first, the overview of quantum computing. And quantum computing relies on quantum mechanisms such as superposition, entanglement, and interference. And here is a very simple illustration of quantum superposition. So for a classical bit, it either stays at a state of 0 or state of 1. And for the quantum mechanical bit or qubit, and we can draw the states as if in the so-called Bloch sphere and represent the north pole as a 0 state. Okay? For example, in the spin system, this can be corresponding to an upspin configuration. Okay? And the south pole is 1 state. Okay? And in the spin configuration, this can be a downspin state. And the quantum mechanics allow a state to be simultaneously at 0 and 1, or in the superposition state between this 0 and 1 state. And for a larger quantum system consisting of multiple qubits, for example, on the right side, we show a case of 3 qubits. And the Hilbert space expands to a size of 2 to the power n. In this specific example, it's 8 states. Any quantum operations on these quantum states can be simultaneously operating on the superposition state on this large space. So if the number of the qubits grow and the size of this computation space becomes exponentially larger, so this is extremely important for offering the massive parallel computing power of quantum computing. So the vision offered in recent history of quantum computing starts from Richard Feynman. So notice that if you want to make a simulation of nature, and you'd better make it quantum mechanical in simulation. And more recently, the progress, for example, includes Shor's algorithm proposed by Shor in 1994 and experimentally demonstrated for a small number, like factoring number 15 by IBM on a quantum computer. And more recently, it includes the demonstration of so-called quantum supremacy. Yeah, in other words, quantum power greatly outperforms classical or even achieves something not possible by classical in 2019. And the recent simulations of molecules in 2020, and as well as demonstration and illustrations of challenges coming up. For example, one of the biggest challenges is really the quantum error and the need for quantum error correction. So there are a lot of applications for quantum computing, and here I just listed a few. For example, performing quantum simulations to design protein and new drugs, design new fertilizers important for agriculture, design new materials like high temperature superconductors for energy applications, and security applications are cryptography, and the long-term weather forecast, finance applications, and so on. So on hardware side, there are many ways to implement a quantum computer, including so-called superconductor-based, semiconductor-based, ion or neutral atom based, as well as optical based platform. Right? So these quantum systems have all been recently explored, intensively explored for in hardware realization of a quantum computer. So next I discuss semiconductor-based quantum computing. So semiconductor-based computing essentially create quantum confinement in silicon or in other semiconductor materials. So we have artificial atoms or molecule structures. For example, we can have defect centers in semiconductors. We can also use gates to create quantum confinements for a semiconductor quantum dot structure. And these structures form contact orbitals, and in which spin, charge, or valid degree of freedom can be qubits. Right? And the quantum computing requires controlled initialization, manipulation, and the readout of this quantum state. Right? And typically in semiconductor-based quantum computing, to keep the quantum information, extremely low temperature is required. We are talking about temperature of tens of millikelvin, right? And typically less than 1 Kelvin. Right? So the material choice are really important. And for example, here are just a list of common materials. Right? And for gallium arsenide, initially employed in this demonstration of semiconductor quantum dot-based quantum computing, and due to lighter effective mass, it's easier to create quantum confinement and quantum tunneling. Right? But due to strong interaction with nearby nuclear spins, the decoherence time, or how long the quantum state can be there, is relatively short. Right? Switching from gallium arsenide to silicon improves the decoherence time considerably. Right? By taking away all the isotopes with nuclear spins from the silicon and create isotopically purified silicon-28. And the coherence can be extended by orders of magnitude. So this is extremely important for quantum computing, as one of the major challenges is how to keep the quantum information coherent and stay long enough time so that quantum computing operations can be performed. So one attractive feature of quantum computing based on semiconductor is to leverage it with existing semiconductor technologies. Okay? So left side, you see a diagram of Intel type of tri-gate transistor, and the right side, you see a typical quantum gate configuration. And here what we have is using the plunger gate to create the quantum dots, and the barrier gate to modulate the barriers that confine these quantum dots. By modulating the barrier height, the coupling between two nearby electron spins can be strengthened or weakened so that entanglement can be modulated. And very often, microwave signals is used also to control and rotate the electron spin here. So semiconductor-based quantum computing can enjoy the potential of a very high integration density or electrical control and the low fabrication cost thanks to the maturity of semiconductor fabrication technology. So in spin-based quantum computing or other quantum computing technologies, and it's important to demonstrate the capability to achieve single spin rotational quantum gates. And in this case, what we see is the spins in the semiconductor quantum dots can be modulated and rotated around a certain direction and operate for many iterations or oscillation periods. And we also require the capability to entangle two nearby spins together. So finally, I'll briefly talk about our work on modeling and the design of semiconductor-based quantum gates. And one approach to use this essentially take advantage of a so-called technological computer-aided design, but adopt it to so-called quantum platform. Okay? So we solve quantum mechanical equations and the quantum dynamic equations to model the quantum confinement and the evolution control readout of spin informations for a spin confined in the quantum dot structure. And we just explore important figure of merits, such as the fidelity of the quantum gates. In other words, how accurate these quantum gates can operate in the presence of various quantum noise. Okay? And the right side, what you see is the idea of a concept of using quantum computer to simulate spin qubits or other quantum gates. Okay? So this is based on the fact that recent quantum computers can already operate, but the spin coherent time or other coherence time on quantum computer is relatively short. So what we use is take advantage of optimization capability developed in classical computer and iteratively optimize the solutions and couple it with a quantum computer to model and simulate quantum states. Okay? So finally, this is a tool we deployed on the Nano Hub, and it can be run online and with a graphical interface and widely used by users worldwide. So if you are interested, welcome to explore these tools. Okay? Thank you very much for your attention.